In 1950, a man named Alan Turing posed a strange question. Can machines think? That question didn't emerge from thin air. Turing had just spent years helping to crack the Enigma code in World War II, building one of the earliest electromechanical computers to do so. But after the war, his curiosity shifted from decoding secret messages to decoding intelligence itself. To Turing, intelligence wasn't magic. It wasn't some spiritual property you could bottle or bless into a machine. It was behavior, patterns, decisions. And if you could describe those decisions with mathematics, you could potentially teach a machine to think. This idea became known as the Turing test, a hypothetical scenario where a human would converse with an unknown entity through a computer terminal. If the human couldn't reliably tell whether they were talking to another person or a machine, the machine would be said to think. That might sound like a philosophy problem, but Turing saw it differently. He saw it as a math problem. Let's be clear. Artificial intelligence isn't just about mimicking the mind. It's about distilling the rules of intelligence into a system that follows logic, updates its beliefs, and refines its behavior based on experience, mathematically. And yet, AI didn't blossom overnight. In 1958, Frank Rosenblatt proposed the perceptron, an early neural network that could perform basic pattern recognition. Its design was beautifully simple. Inputs went in, were weighted, summed up, and passed through a threshold. If the total exceeded that threshold, it would fire a signal. If not, it stayed silent. It was inspired by the brain, but powered by math, specifically linear algebra and weighted summation. Rosenblatt hoped it would someday learn to recognize faces, understand speech, maybe even learn language. But the optimism didn't last. By the 1970s, interest in AI plummeted. The perceptron had limitations. It couldn't even solve the basic XOR problem, which involves two binary inputs that only return true when they're different. Mathematically, a single-layer perceptron couldn't model it, a discovery that temporarily killed the hype. It wouldn't be until the 1980s that the concept of backpropagation, a way to train multi-layer neural networks, reignited the field. Suddenly, AI systems weren't limited to linear patterns. They could learn non-linear relationships, complex mappings, language, vision, strategy. Then came the 2000s, when faster computers and massive datasets fueled an explosion in machine learning techniques. By 2012, a deep neural network called AlexNet shattered records in an image recognition competition. It didn't just work, it blew away everything before it. And that's when people started to take AI seriously again. From your smartphone's autocomplete to voice assistants, facial recognition, fraud detection, and ChatGPT. You're surrounded by systems that rely on something deeper than code. They rely on math. So, how exactly does math enable intelligence? What makes a neural network learn? What's hiding behind terms like backpropagation, softmax, gradient descent, or attention? Is it just equations and tensors flying around? Or is there a deeper structure, a mathematical blueprint, that allows machines to transform raw data into decisions? That's what we're here to explore. We'll walk through the mathematical layers that make AI tick, starting with the backbone of all machine learning systems, linear algebra. If data is the fuel of AI, then linear algebra is the engine. It's the system that takes raw information and turns it into structured meaning, numbers into decisions, pixels into patterns, sounds into sentences. But to understand why linear algebra is so essential to artificial intelligence, we first need to ask a deceptively simple question. What does a computer actually see when it looks at the world? Not colors, not emotions, not meaning. It sees numbers. When you show a machine an image, that image becomes a matrix, a grid of pixel intensities. When you feed it text, that text becomes a vector, a sequence of numerical embeddings. Even a sound clip, like someone saying hello, is transformed into a time series of amplitudes. Once again, just numbers. But numbers alone are useless without structure. That's where linear algebra comes in. Let's start with the vector. At its core, a vector is just an ordered list of numbers. But that simple definition hides an enormous amount of power. Imagine you want to represent the color of a single pixel on your screen. You might store it as a vector like this. That's a bright red pixel using RGB values. Now imagine a word like cat. A computer might represent that as the following. This is a word embedding, a dense vector that encodes the meaning of a word based on how it's used in language. These vectors aren't just random. They're learned, adjusted during training to reflect semantic relationships. For instance, the vector for king minus man plus woman gets you close to the vector for queen. That's not magic. It's geometry in high-dimensional space. These vectors don't live in a world of two-dimensional graphs or cute arrows on paper. They exist in hundreds or thousands of dimensions. And AI systems navigate that abstract space with surprising fluency. If vectors represent individual data points, then matrices represent transformations between them. Take a vector, multiply it by a matrix, and you've just changed something fundamental. Rotated it, scaled it, projected it into a new space, and linearly combined its components. In AI, this operation is at the heart of everything. Every layer in a neural network applies a linear transformation to its inputs. This means, take a vector of inputs, multiply it by a weight matrix, and pass the result through a nonlinear function. Let's say your input vector has 5 values, maybe representing pixel intensities or sound features. A matrix with 5 columns and 10 rows can project that 5D vector into a new 10D space. Output equals matrix multiplied by the input vector, which equals the output vector. This is how one layer of a neural network produces the input for the next layer. It's not a metaphor. This is literally how the machine thinks. Layer after layer, the system composes complex functions from stacked linear operations, followed by nonlinear activations. And thanks to the associative properties of matrix multiplication, these operations are fast to compute, easy to optimize, and friendly to parallel hardware like GPUs. Now let's zoom into the most fundamental operation, the dot product. If you take 2 vectors and compute their dot product, you're doing something very specific. You're measuring their alignment. The dot product answers this question: how much does one vector agree with the direction of another? Mathematically, it's represented by the following, where theta is the angle between the 2 vectors. In AI, this is everywhere. For instance, in word embeddings, dot products measure semantic similarity between words. In attention mechanisms, dot products determine which parts of the input to focus on. In classifiers, dot products drive the decision boundaries between categories. Imagine a spam filter. You might represent an email as a vector of word frequencies. You then dot that with a spam weight vector. If the result is above a certain threshold value, the system predicts spam. Otherwise, the email is considered safe. Dot product equals decision. And the whole thing is fast, a single line of code, executed billions of times a second. At some point, vectors and matrices aren't enough. You need to represent more complex structures. A video, which is frames multiplied by height, multiplied by width, multiplied by RGB channels. A batch of text samples, which is samples multiplied by words, multiplied by embeddings. Or a sequence of feature maps in a convolutional neural net. This is where tensors come in. A tensor is just a multi-dimensional array. A scalar is a 0D tensor, a vector is a 1D tensor, and a matrix is a 2D tensor. A 3D tensor might look like a cube of values. 4D, 5D, and beyond. Those live in the invisible world of deep learning. Tensors allow AI systems to process entire datasets at once, complex spatial temporal data, and parallel operations across multiple samples. And because linear algebra generalizes to tensors, all the same rules apply, just with more axes. If linear algebra is the language of AI, then calculus is its sense of direction. Without calculus, a neural network could exist, but it would be frozen in place, unable to improve, adapt, or refine itself. At its core, learning in AI is about adjusting parameters so the model performs better over time. And the mathematical framework that tells us how to adjust them, that's calculus. Every AI system has a goal: to correctly classify an image, predict the next word, translate a sentence, or forecast tomorrow's weather. But the first time you feed data into a newly initialized neural network, it's basically guessing at random. It produces an output. You compare it to the correct answer and measure the error using a loss function. Example: if you're teaching a model to recognize cats, you might use cross-entropy loss, which penalizes wrong guesses more heavily when the model is confident but wrong. This loss function is just a mathematical formula that outputs one number: the cost of being wrong. Lower is better. So the learning problem boils down to: find the set of weights and biases that make the loss as small as possible. In everyday life, if you want to make a hill climb easier, you'd look for the slope, how steep it is, and in which direction it rises. In machine learning, derivatives are our slopes. A derivative measures how much a change in one variable affects another. If your loss function depends on millions of weights, you want to know: if I nudge this weight a tiny bit, will the loss go up or down, and by how much? That's the role of the partial derivative. It looks at one weight at a time while holding others constant. Now, here's the problem. Neural networks don't live in two dimensions like a hill. They exist in a parameter space with millions or billions of dimensions. You can't just look around and see the slope. Instead, we calculate the gradient, a vector that points in the direction of steepest descent in this high-dimensional landscape. If ascent is uphill, we want the opposite, the direction of steepest descent, because we're minimizing the loss. So learning becomes: 1. Compute the gradient of the loss with respect to all parameters. 2. Move a tiny step in the opposite direction. Do this over and over, and the network gradually descends into a valley where the loss is low. Gradient descent is the workhorse of machine learning. It's an iterative algorithm that updates weights like this: new weight equals old weight minus learning rate, multiplied by gradient. Learning rate controls how big your steps are. Too big, you overshoot and bounce around. Too small, you crawl toward the solution and waste computation. Variants like stochastic gradient descent, atom, and RMS prop tweak this process to handle noisy data, adapt the learning rate, or converge faster. Computing a gradient for millions of parameters sounds impossible unless you have a trick. That trick is backpropagation, invented in the 1970s, but popularized in the 1980s. It uses the chain rule from calculus to break complex functions into smaller parts, each with its own derivative. Imagine the network as a stack of functions. The chain rule lets you work backward from the loss to figure out how each layer contributed to the error. Instead of recalculating everything from scratch for each parameter, you reuse intermediate results, making it computationally feasible. Without calculus, you wouldn't know which direction to adjust weights, you wouldn't know how much to adjust them, and learning would be blind trial and error, and hopelessly slow. With calculus, models improve continuously, training can scale to massive datasets, systems adapt to new patterns over time. Think of it this way. Linear algebra gives AI the framework to process information, while calculus gives it the feedback loop to refine that process. Probability and statistics give AI the ability to make decisions when the outcome is uncertain. In the real world, data is messy, incomplete, and often noisy. Machines need a mathematical way to handle that uncertainty. Probability theory provides the framework, and statistics provide the tools to apply it to real data. Every AI system that makes predictions is essentially dealing with probabilities. A model that predicts the weather does not say, "It will rain tomorrow." It says, "There is a 70% chance of rain tomorrow." This distinction is important. The model is not certain. It is estimating the likelihood of an outcome based on the data it has seen. In probability theory, a random variable is a quantity whose value depends on chance. There are two main types. A discrete, random variable can take on specific, separate values, such as the number of heads when flipping a coin 3 times. A continuous random variable can take on any value in a range, such as the exact temperature tomorrow. The behavior of a random variable is described by its probability distribution. This is a mathematical function that assigns a probability to each possible outcome. Common examples include the Bernoulli distribution for binary outcomes like yes or no, the normal distribution, also called the Gaussian, for continuous data that clusters around a mean, and the categorical distribution for multiple discrete outcomes. In AI, probability distributions appear everywhere. They are used to model uncertainty in measurements, to generate predictions, and to decide how confident the model is in its output. One of the most important tools in probabilistic reasoning is Bayes' theorem. It describes how to update the probability of a hypothesis when new evidence is observed. The formula is probability of A given B equals the probability of B given A times the probability of A, divided by the probability of B. Here's how it works in practice. Suppose an email filter is designed to detect spam. The hypothesis is, this email is spam. The evidence is that the email contains the word lottery. P of A is the prior probability that an email is spam before considering this email. PB given A is the probability that a spam email contains the word lottery. PB is the probability that any email contains the word lottery. By applying Bayes' theorem, the filter updates the probability that the email is spam given the observed word. This updating mechanism is fundamental to many AI systems. It allows them to combine prior knowledge with new data in a mathematically consistent way. Two important statistical measures in AI are expectation and variance. The expectation, also called the mean, is the average value a random variable takes over many trials. It tells the model what to expect on average. The variance measures how spread out the values are from the mean. A small variance means the data points are close to the mean. A large variance means they are more widely spread. These measures are critical in decision-making. For example, in reinforcement learning, an agent may choose an action that maximizes expected reward, but also considers the variance to manage risk. In many AI tasks, especially classification, the model's output is a set of probabilities over possible classes. For example, an image classifier might output cat 0.85, dog 0.10, rabbit 0.05. This means the model estimates an 85% chance the image is a cat. The decision rule is often to choose the class with the highest probability. However, the probability distribution also tells you how confident the model is. If the highest probability is only 0.4, the model is much less certain. Randomness is not just noise to be removed. It is also used as a feature in training. Random initialization of weights helps neural networks avoid symmetry problems. Random shuffling of training data prevents the model from learning spurious patterns. Random dropout of neurons during training helps prevent overfitting. Statistical sampling methods such as Monte Carlo simulations, use randomness to estimate values that would be difficult or impossible to compute directly. This is widely used in areas like reinforcement learning, where the environment is too complex for exact calculation. Probability and statistics give AI the ability to operate in uncertain environments. Probability distributions describe the possible outcomes. Bayes' theorem updates beliefs when new evidence appears. Expectation and variance measure central tendency and spread. Probabilities and classification give both a decision and a confidence level. Randomness, when controlled, can improve learning and generalization. Without probability, AI would be limited to perfect, noise-free situations, a world that does not exist. With probability, it can make reasoned choices in the face of incomplete information. Loss functions and backpropagation are two of the most critical components in training an AI model. The loss function measures how far the model's predictions are from the correct answers. Backpropagation is the algorithm that uses this measurement to adjust the model's parameters so that future predictions improve. The loss function is a mathematical formula that takes in the model's predictions and the correct answers, then outputs a single number representing the error. Lower values mean better performance. Different tasks require different loss functions. For regression tasks, where the output is a continuous value, a common choice is mean squared error. It is calculated as the average of the squared differences between predicted and actual values. Squaring penalizes larger errors more heavily. For classification tasks, especially those with multiple possible classes, cross-entropy loss is widely used. It measures the difference between the predicted probability distribution and the actual distribution, which is typically a one-hot vector representing the correct class. For binary classification, binary cross-entropy is used. It is a simplified version of cross-entropy for two-class problems. The choice of loss function matters. It defines what better means for the model and determines how the model will prioritize improvements. Once the loss is calculated, it acts as feedback. The goal is to adjust the model's weights and biases so that the loss decreases. The loss function is connected directly to the model's parameters through the computations performed during the forward pass. By applying calculus, specifically derivatives, we can determine how a small change in each parameter would affect the loss. Backpropagation is the algorithm that efficiently calculates these derivatives for all parameters in the network. It relies on the chain rule from calculus, which allows us to compute derivatives of complex nested functions. The process works in two main steps. 1. Forward pass. Input data flows through the network. Each layer transforms the data using its weights and biases, producing an output. The loss is computed based on this output. 2. Backward pass. Starting from the output layer, the algorithm works backward through the network, calculating the gradient of the loss with respect to each parameter. The chain rule is used to break this calculation into manageable parts, reusing results from earlier steps to avoid redundant computation. This method ensures that we can calculate the gradients for millions or even billions of parameters in a reasonable amount of time. Once the gradients are known, they are used by an optimization algorithm, such as stochastic gradient descent, or ADAM, to update the parameters. New weight equals old weight, minus learning rate multiplied by gradient. The learning rate determines how large each adjustment step is. A learning rate that is too high can cause the model to overshoot the optimal values. A learning rate that is too low can slow down training significantly. Backpropagation is efficient because it avoids recalculating the same intermediate values multiple times. Instead, it stores these values during the forward pass and reuses them during the backward pass. It is also general. The same algorithm can be applied to any differentiable model, regardless of its architecture. This is why it has become the standard method for training neural networks. The loss function defines the objective for the AI model. Backpropagation is the mechanism that connects this objective to the model's parameters, enabling learning. Together, they form the feedback loop that allows the model to improve with each training iteration. Without a loss function, the model would have no sense of how well it is performing. Without backpropagation, adjusting the parameters to improve performance would be computationally infeasible. Modern AI is driven largely by deep learning. Deep learning refers to neural networks with many layers, sometimes dozens, sometimes hundreds, that can automatically extract and combine features from raw data. This approach has enabled breakthroughs in image recognition, speech recognition, natural language processing, and many other fields. A deep neural network is made up of multiple layers of interconnected nodes, or neurons. Each layer transforms its input into a new representation before passing it to the next layer. There are several common types of layers. Fully connected layers. Each neuron connects to every neuron in the previous and next layer. These are standard in many models. Convolutional layers. Used mainly in image processing. They scan small regions of the input with filters, extracting local patterns like edges, textures, or shapes. Recurrent layers, designed for sequential data, such as text or time series. They maintain a form of memory from previous steps. Attention layers allow the network to focus on specific parts of the input, improving performance on complex tasks like translation. Deep learning works well because each layer learns increasingly abstract features. For example, in image classification, the first layers may detect edges, the next layers detect shapes, and the later layers detect entire objects. The core ideas behind deep learning have existed for decades. The recent explosion in capability is due to three factors. 1. Data availability. Modern systems can be trained on massive datasets, containing millions or billions of examples. 2. Hardware advances. Graphics processing units and specialized hardware like TPUs are optimized for the matrix operations that deep learning requires. 3. Algorithmic improvements. Techniques like batch normalization, dropout, and advanced optimizers help train deeper networks more effectively. In 2017, a new architecture called the transformer revolutionized natural language processing. Unlike recurrent networks, which process sequences step by step, transformers process all elements of a sequence in parallel, using an attention mechanism. The key idea is self-attention, which calculates how much each element in a sequence should attend to every other element. This allows the model to capture long-range dependencies and contextual relationships efficiently. A transformer is made up of layers containing multi-head self-attention, feed-forward networks, and normalization steps. Multi-head attention means that the model can focus on different types of relationships at the same time. Transformers have enabled the development of large language models, or LLMs. These models are trained on vast amounts of text and can generate coherent, contextually appropriate responses to prompts. Examples include GPT models, BERT, and T5. They can write essays, answer questions, translate languages, and even generate code. The training process for an LLM involves predicting the next word in a sequence, given all the previous words. By doing this at a massive scale, the model learns grammar, facts, reasoning patterns, and even some forms of creativity. Recent research has extended transformer architectures to handle multiple types of data at once. Multimodal models can process and relate text, images, audio, and even video. For example, a multimodal system could take a photo, generate a caption, and then answer follow-up questions about the scene. This requires integrating visual and language understanding in the same network. While deep learning and transformers have enabled unprecedented capabilities, they have limitations. They require enormous amounts of data and computing power. They can produce confident but incorrect answers. They may encode biases present in their training data, and their decision-making process is often opaque, making them difficult to interpret. Research is ongoing to address these issues through better data curation, interpretability tools, and more efficient architectures. Modern AI is dominated by deep learning, with transformers leading the way in language and multimodal applications. These systems leverage massive data sets, powerful hardware, and advanced architectures to achieve state-of-the-art performance across many domains. The principles remain the same. Process data through a series of learned transformations, optimize using calculus-based methods, and rely on linear algebra as the computational foundation. What has changed is the scale, efficiency, and sophistication of the models. Artificial intelligence is no longer just a research project. It is part of daily life, powering search engines, voice assistants, recommendation systems, fraud detection, and more. As these systems become more capable, it is essential to examine their ethical implications, limitations, and possible future developments. Models learn from data. If the data contains biases, the model can learn and amplify them. This can happen in many forms. Selection bias. If the dataset does not represent all groups equally, predictions will be skewed toward the overrepresented groups. Label bias. If the labels in training data are incorrect or subjective, the model will learn those errors. Historical bias. If the data reflects historical inequalities, the model may perpetuate those patterns. For example, a hiring algorithm trained on historical data from a company may learn to favor certain demographics if that was the trend in the past. Preventing bias requires careful dataset curation, fairness-aware algorithms, and continuous monitoring. These models often rely on large datasets containing personal information. If this data is not handled properly, it can lead to privacy violations. Two major risks are: 1. Data leakage. Sensitive information unintentionally stored or revealed in the model's parameters. 2. Re-identification. The ability to match supposedly anonymous data back to specific individuals. Techniques like differential privacy and federated learning aim to protect privacy by limiting how much individual data influences the model. Many modern AI models, especially deep neural networks, operate as black boxes. They can make accurate predictions, but their internal decision-making process is difficult to interpret. This lack of transparency creates problems in critical areas like healthcare, finance, and criminal justice, where stakeholders need to understand why a decision was made. Explainable AI is an active research area that seeks to make model outputs more understandable. Methods include feature importance scoring, visualizations, and simplified surrogate models. Systems can be brittle. Small changes to input data, known as adversarial examples, can cause large and unexpected changes in output. For example, adding imperceptible noise to an image of a stop sign can cause a vision model to misclassify it as a speed limit sign. In safety-critical applications like autonomous vehicles, such vulnerabilities are unacceptable. Robustness research focuses on making models less sensitive to small perturbations and more resilient to unexpected inputs. Training large AI models can require significant computational resources, which in turn consume large amounts of energy. This raises concerns about the environmental footprint of AI research and deployment. Efforts to address this include more efficient algorithms, model compression and pruning, and use of renewable energy for data centers. Several trends are likely to shape the future of these systems. Smaller, more efficient models. Researchers are working on ways to deliver high performance without massive size, making AI more accessible and sustainable. Improved generalization, moving toward models that require less data to learn new tasks, closing the gap between human and machine learning efficiency. Better integration of symbolic reasoning, combining statistical learning with symbolic logic to improve reasoning and reduce reliance on pattern recognition. Expanded multimodal capabilities, building systems that seamlessly integrate text, images, audio, video, and other data types. Increased regulation and governance. Governments and international bodies are beginning to develop policies to ensure responsible AI development and deployment. Ethics and limitations are not side issues. They are central to its safe and beneficial use. Addressing bias, privacy, transparency, reliability, and environmental impact is critical as these systems become more powerful and integrated into society. The future of AI will depend not just on technical advances, but on responsible choices made by researchers, companies, and policymakers. Artificial intelligence often feels like a field of infinite complexity, full of algorithms, architectures, and emerging techniques. Yet, at its core, it is still driven by mathematics. Every prediction, every decision, and every adjustment made by a model is the result of mathematical operations. From the very beginning of this discussion, we have seen that the building blocks of AI come from three key areas of mathematics. 1. Linear algebra. This is the language of data representation and transformation. Vectors, matrices, and tensors store and manipulate the information that flows through a model. 2. Calculus. This provides the tools to optimize models. Gradients and derivatives tell the system how to adjust parameters to improve performance. 3. Probability and statistics. These allow the models to operate in uncertain environments, make predictions, and quantify confidence. These areas work together. Linear algebra structures the data, calculus refines the model's behavior, and probability manages the uncertainty. The rapid advances in AI over the past decade have not changed the fact that mathematics is the underlying engine. Even the most advanced architectures, such as transformers and multimodal networks, rely on the same fundamental concepts. The attention mechanism in transformers is built on dot products and vector normalization. Gradient descent, used to train every modern model, is an application of multivariable calculus. Softmax outputs and classification are based on exponential functions and probability theory. These are not just theoretical concepts, they are the operational rules of the systems. One reason mathematics is sometimes overlooked in discussions about AI is that it is often abstracted away by libraries and frameworks. A developer using PyTorch or TensorFlow may call a single function to perform an operation that, under the surface, involves thousands of matrix multiplications and derivative calculations. This abstraction is useful, but understanding the math gives a deeper sense of control. It allows for informed choices about model architecture, optimization strategies, and evaluation methods. Mathematics in AI is not static. Researchers continue to adapt and extend mathematical tools to meet new challenges. Examples include novel optimization algorithms that improve convergence speed and stability, new probability models that better capture uncertainty, efficient linear algebra techniques for working with extremely large datasets. The field evolves, but the foundation remains. Mathematics provides the framework for innovation. As these systems continue to expand into more aspects of society, the need for mathematically grounded understanding will grow. This is important for several reasons. Interpretability. Understanding the math helps explain model behavior to users and stakeholders. Reliability. mathematical insight helps identify weaknesses and design robust systems. Ethics and governance. Many fairness and accountability metrics are mathematical in nature, requiring clear comprehension to implement effectively. In other words, the responsible development of AI depends on more than code. It depends on the principles that code is built upon. Artificial intelligence can be described in many ways, as a set of algorithms, as a technological revolution, or as a tool for solving problems. But no matter how advanced the systems become, they will remain grounded in the same mathematical principles. Every layer of a neural network is a set of equations. Every parameter update is a calculus operation. Every probability output is a statistical statement. Math is not just part of artificial intelligence. Math is the structure that makes artificial intelligence possible. Hey everyone, thank you so much for watching. This is one of my first attempts at creating an in-depth long-form style video, and it took a considerable amount of work and research to put together. If you enjoyed it and would like to see more content like this, consider subscribing. I have plenty more videos planned for the future.